One of the things that we will often do with a piecewise function is call out one special point on a graph. Now, in real life, we usually do that because something is wrong with that point. For example, that point is not in the domain of the function that we're otherwise using. However, for practice with the notation, we can also just call out some random point, as we do in this example. When we have a piecewise function like this, where our function has one definition for almost all values of x, and another definition for one or a few specified values of x, the first thing we do is to graph the main function, the one that applies for most values of x. So ignore those weird points for the moment, and just sketch the graph of x squared minus 2. Now this function is quadratic, and we see that nothing's being added to or subtracted from x before it's squared. So our vertex is at x equals 0, y equals negative 2. We'll go ahead and put that on the graph. And that's an ordinary point. And then if x is 1, then y is 1 squared minus 2 is negative 1. So our parabola will go through this point. If x is negative 1, y is negative 1 squared minus 2 is also negative 1. Again, we could also do this by transforming functions. We notice that this is just the standard parabola translated down 2 units. So we could plug in one more point, or we could just sketch kind of a basic parabola shape. Either way, there we go. Okay, next, we drew a point on our graph that isn't really there. We drew in the point where x equals 1, even though that's really not part of our graph. We want to make a hole in this curve that we just drew at the point where x equals 1. So I'm going to just go to the point on this curve where x equals 1 and make a hole in my graph. Now, if you are mildly obsessive, you might erase the part of the graph that passes through the hole, but that is really not necessary. So now we have a hole in our graph indicated by this empty circle. This empty circle indicates that the point 1, negative 1 is not part of our graph, even though nearby points are. And now we plot instead this special point. Our function says when x equals 1, f of x equals 3. So the point 1, 3 is on our graph. We'll put a filled in dot up here at 1, 3. What this function expression is telling us is that our function quietly ambles along, being a parabola, until it gets to 1, where it suddenly jumps up to 3, then jumps back down, and continues to amble along, being a parabola. One mistake I sometimes see students make in graphing something like this is to fill in this line. You don't want to fill in that line because that's a vertical line. This would not be a function then. This doesn't tell us that when x equals 1, y takes every value from negative 1 up to 3. It just tells us that when x equals 1, y should be 3. Okay, so that's knocking a hole in a graph for one special point, which again, When we do it in real life, we usually have some reason for it. There's something going wrong at that special point. But we can just do it too. And so we're doing this really to practice our skill at using this notation. The special point might also come at the end of other pieces. In this example, our graph is divided into 3 parts. We have a piece to the left of -2, a piece right at -2, and a piece to the right of -2. So piece number 1 is the part where x is less than -2. And on this part, f of x equals 3. That's a constant function. Its graph is going to be the horizontal line at 3. And so we'll draw a horizontal line at 3, and the end point will be -2, 3. Because x is not allowed to equal -2, that's going to be empty. So I'll put an empty circle at -2, 3, and then draw the horizontal line to the left of that. Why to the left? Because this part of the graph is where x is less than -2. The second part of our graph is where x equals -2. And we're told that where x is -2, f of x is equal to -1. But x equals -2 is just one x value. So this is just one point. This is just the point -2, -1. So we'll draw a filled in dot here to indicate that point. The third part of our graph is where x is greater than -2. And on this part of the graph, f uses the expression x plus 3. One end of that is going to be where x is -2. So we'll evaluate the function at -2 using this formula, and we'll have the point -2, 1. And then we need some other point over in this third region. So some point where x really is greater than 2. I'm going to pick 0. I always like to do arithmetic with 0 if I possibly can. F of 0 is 0 plus 3 is 3. So that'll give me the point 0, 3. Again, I could have picked any x value I liked. I picked that one because I like to do arithmetic to 0. Okay, how will I represent this on the graph? Well, -2 is not included in this part, so this point is out. And then this is not an endpoint, so it's in, but it's ordinary. I'm not going to put a big filled dot there. I'm just going to put an ordinary point there. So at -2, 1, I'll put an empty dot. Notice I have 2 empty dots and a filled in dot all lined up on this vertical line. Only the filled in dot is actually a point on this graph, so this passes the vertical line test. And then I have another point at 0, 3, and I'll draw the line through those 2 points, and that's the rest of my graph. And I'm done. So when the singled out point comes between 2 other pieces, we don't need to worry about it so much, as long as we can realize that that piece of the graph consists only of one point.